Welcome to the UEI Technical Master Class. I'm Bob Finn with UEI, and I hope everyone is doing well. Today's webinar is entitled Keep Your Vehicle Deployment on Course: How to Design, Test, and Implement an Efficient Control and Monitoring System. Our presenters today will be our own Chris Hallinan, Shweta Bhadravati Patil from Mathworks, and Dan King from RTI. In this masterclass, our three presenters will discuss how model-based design is transforming the way engineers and scientists plan, build, and test their systems. Okay, got a lot of content to share with you today, so I'm going to wrap up my introduction, and without further ado, I'm going to hand this over to you, Chris.
Thanks, Bob. Greetings, everyone. Again, my name is Chris Hallinan, and I'm the Southeast Regional Sales Manager for UEI. Thanks for taking time out of your day to join us. I'm excited about today's masterclass. We're bringing together two of our partners who bring great value to those of you doing hardware in the loop, software in the loop, or any kind of design targeting complex hardware systems such as aircraft, rockets, trucks and automobiles, manufacturing plants, power generating systems, and more. You'll see how MATLAB and Simulink, together with RTI Connectivity Framework, can be used with UEI hardware to enable rapid development, accurate modeling, and ultimately successful deployment on real hardware. And don't forget, you can ask questions in the chat box as we go along. You don't have to wait until the end of the presentation to ask your question. So go ahead and, if you have a question during the presentation, go ahead and type it into the chat box and we'll be sure to get to it. Today's masterclass will talk about model-based design, using vehicle design concepts to highlight the many benefits of model-based design, simulation, and deployment. We'll take a look at a high-level overview and introduce model-based design using UEI's rugged deployable hardware, the Mathworks, MATLAB, and Simulink, and embedded code generation, and RTI's connectivity framework called Connext DDS. We'll discuss the benefits of model-based design and show you direct examples of how to build deployable systems using UEI hardware, MATLAB and Simulink for algorithm design, code generation and deployment, and RTI for data distribution around the system. Getting your vehicle off the ground can be challenging and fraught with complexity. Whether you're building a helicopter, a jet, a rocket, or an autonomous electric vehicle for land, sea, or air, they all need control and feedback points to stay on course. Complete control systems, individual components, an entire manufacturing plant can be prototyped on a desktop and deployed on real hardware. You can then distribute the application on everything from the physical system, the device, the plane, the ship, whatever, to a hardware-in-the-loop test station. Using modeling and code generation technology from the Mathworks, real hardware deployment options from UEI, and connectivity framework from RTI, you'll learn how to move your system from design concepts to land, sea, air, or space deployment. In this high-level diagram, consider that each hardware chassis, populated with a variety of I/O interfaces, including synchro resolvers, analog and digital I/O, and avionics interfaces, to name a few, is running a model developed in Simulink using Connext DDS for data movement among the systems to the central simulation or HMI or processing element. There are obviously many benefits to simulation as part of the development process, and even as a critical element in ongoing design and maintenance of large, complex systems. Simulation has the potential to save significant time, money, and resources. Often, even complex hardware subsystems can easily be modeled with COTS or commercial off-the-shelf equipment. Using COTS hardware to simulate actual subsystems can be extremely cost-effective, enabling the use of multiple simulation stations or multiple labs at a fraction of the cost of real hardware. Significant time savings can be realized by allowing development to proceed well before the real hardware has become available. System functionality can be prototyped and validated prior to development and availability of real hardware. So why simulate? There are many benefits of simulation. Along with time and cost benefits, simulation has the potential to vastly improve development accuracy. Corner cases can be evaluated, and multiple error scenarios can be tested, potentially leading to a much more robust system. This is especially critical in safety-critical systems where errors have the potential for catastrophe. A powerful technique in Hill Labs uses multiplexers in sensor or signal lines, enabling the simulation engine or engineer to switch between the real sensor or hardware subsystem, a simulated sensor or hardware subsystem, or an error injection channel in order to provide maximum flexibility and understand the effects of both real hardware and simulated error conditions. In a similar manner, human factor testing can be simplified and made more robust by providing a wide range of normal and abnormal scenarios for training, crew proficiency, and mission planning. A typical test bench in a Hill lab might contain a mix of real hardware and simulated hardware. Hill, or hardware in the loop, is commonly used in automotive and power plant design applications. One major aerospace manufacturer, which I'm familiar with, a customer that I've visited many times, uses many Hill labs which contain a complete representation of a given model of aircraft. Virtually every system, excluding those that burn fossil fuel, is represented by a combination of real hardware, virtualized hardware, and multiplexers that can present either the real hardware, simulated hardware, or an error injection channel back to the simulation engine. Simulink running on UEI hardware is used to model various hardware or to control signal paths. Sill labs, or systems integration labs, are commonly used in aerospace applications. More often than not, sill labs are used as test, validation, and optimization tools. For example, one military facility I'm involved with makes extensive use of hardware in modeling various rotorcraft. These simulators are routinely used to validate new software loads from the manufacturer in the avionics and flight management computers. Pilots actually fly simulated missions in a variety of mission profiles as part of the validation process in these sill labs. In the next couple slides, we'll look at examples of typical signals used in Hill and sill labs. Thermocouples and RTDs are used to represent temperature inputs. Strain gauges measure force or strain on structures. Synchro resolvers, widely used in aircraft to transmit or measure rotational position. RVDTs and LVDTs are used in a similar fashion for linear motion or position indication. A Hill lab may include general waveforms including phase or amplitude sweeps, simple 4 to 20 milliamp current loops, or plain old analog voltages. Common communication signals used in Hills can include the ubiquitous ARINC 429, used for air data distribution and subsystem communication among avionics devices and more. ARINC 708 453 is a popular format for weather data, including WXPD. ARINC 664/AFDX is another deterministic Ethernet protocol gaining traction in aerospace applications. ARINC 825 is an aerospace implementation of the popular CAN bus. ARINC 629, used on the Boeing 777 and some Airbus aircraft, is an aerospace data bus designed to supersede ARINC 429. And of course, MIL standard 1553 is widely used in military applications, and especially aircraft, but also some ground vehicles. So now let's take a look at what the design process looks like from a model design to production code generation. Later we'll look at how easy it can be to deploy models and algorithms to UEI hardware integrated with RTI Connext DDS using MATLAB and Simulink. I'll now pass the baton to Sweta Bhadravati Patil from the Mathworks. Sweta, it's all yours.
Okay, thank you, Chris. I'm Shweta Bhadravati Patil. I'm a product manager at Mathworks. Today, I'm going to give you an overview of how model-based design can be used for production code generation. Before I get started, I want to tell you how Mathworks model-based design tools has helped many industries, including automotive, aerospace and defense, medical, transportation, and so forth to bring their return on investment. Over here, you can see GM Global Hybrid Powertrain has developed HVAC system using model-based design tools. It not only made development easy to them, but also made it faster while enabling them to verify and test months earlier than they could do it before. Over here, you can see TRW Automotive. They also followed model-based design by performing formal testing in the first phases of development, and it helped reduce their effort from days to hours. Okay, and here there is an example of aerospace industry. Honeywell Aerospace USA has updated a flight control system while reducing development time and costs, and that's by 60%. And here there is an example of medical industry, Weinmann Medical, that develops life-saving transport ventilator using model-based design as well, that has accelerated their development time by 50%. Similarly, there are examples from Alstom Grid UK that makes HVAC power system and Alstom train control system. They both have found the benefits of reducing development time using model-based design. So you can model your algorithm in 3 ways. So let me explain the importance of having all these 3 options. Simulink follows block-oriented approach for system design. It helps you to explore a wide design space by modeling the system under test and the physical plant. Your entire team can use one multi-domain environment to simulate how all parts of the system behave. Then you can package and share your simulations with collaborators, suppliers, and clients. Then Stateflow helps you create state machines for event-based logic. It provides a graphical language that includes state transition diagrams, flowcharts, state transition tables, and truth tables. You can use Stateflow to describe how MATLAB algorithms and Simulink models react to input signals, events, and time-based conditions. You can use MATLAB function block to implement MATLAB functions to simulate models, to deploy code, and embed code in processors. So using MATLAB function block, you can generate readable, efficient, and compact C or C++ code for deployment to desktop and embedded applications. So additionally, you can deploy to many hardware devices using any of the 3 modeling methods. You can generate code in all these 6 languages like C, C++, CUDA, VHDL, Verilog, and structured text from Simulink model. Note that additionally, you can generate portable code, and it is possible to generate target optimized code and real-time schedulers and device driver blocks as well. So Mathworks hardware support packages offer target-specific support for a few devices, but also hardware vendors offer their own support packages for Simulink-based tools. And you can generate code from the MATLAB implementation as well. So that can be portable code for numerical algorithms or desktop applications. You can also generate C or C++ code from Simulink for rapid prototyping, hardware in the loop type of test for real-time machines. And then you can generate production C or C++ code that can be optimized and deployed on the microcontrollers or DSP processors. Additionally, you can perform software in the loop or process in the loop type verification, and then the generated code can be qualified with the Simulink code inspector for the certification and the qualification toolkits. You can also generate CUDA code for deep learning, radar, or vision type of application that can be deployed on NVIDIA, Tegra, Jetson, Xavier, or Nano. Okay, you can use Simulink to evolve models from high-level design to detailed design, as you can see here. and that can be floating or fixed point or doubles or single. So you can make those modification or the settings in the Simulink platform. And then you can check whether this algorithm perform really well on the actual device with true latencies. So that can be extended by doing the prototyping to use with the production hardware. Okay, then once you're happy with the prototyping, you can generate code optimized for production hardware by performing the further optimization options that's available in the code generation settings. That's by without changing the model. Okay, now let me show you an example how we have designed an helicopter control system in Simulink platform. So here we have designed a helicopter control architecture using System Composer. It is a fairly new tool for authoring system and software architecture. Over here, the flight control computer is taking pitch, roll altitude, and yaw rate based on pilot inputs from the cyclic and pedals, maybe over airing 429. Then flight control computer is sending the actuator input, that's probably via DDS. Then hydraulic actuator sends the processed data to helicopter and sends the feedback via AHRS sensors back to the flight control computer. So the flight control computer closes the loop on 3 hydraulic actuators and as sensor inputs from 3 altitude heading reference systems. All the architecture models are linked to an Simulink model. Let me open the flight computer model. Over here, let me generate production code with embedded coder. Then open the configuration parameter settings so that I can choose code optimization options to generate optimized code. Okay, now let me hit build button. Notice that code is generated. Let me check code for actuators. Looks great. Now let me check code for helicopter inner loop and outer loop. The generated code is qualified for use with Devo qualification kits using Simulink Code Inspector. To do further verification, you can test code, especially on a target-specific hardware. That's by doing PIL, that's processor in the loop. Or if you want to do it without the target, then you can do the software in the loop verification. That helps you to verify, does your code behave like model, and you can further optimize the resources. Furthermore, to test system faults, you can run it using hardware in the loop simulation. You can do hardware in the loop using variety of solutions, including UEI or hardware. Okay, so the production code generation from Simulink models are compliant to many software and safety standards, including ODSR, ISO 262, DO 178, and IEC certifications. All right, this ends Mathworks' presentation on overview of MBD for the production code generation. Thank you.
Thank you, Sweta. In many cases, systems can be much more distributed. Nearly everyone is familiar with and has likely been involved in programs with remote workers and remote development facilities. In fact, I'd venture to guess that it's pretty much the norm now, even for small companies. Those remote facilities might be down the road or across an ocean. Different hardware subsystems can exist across the room or in a remote lab. How can we move data and information between systems and models? How can we make it easy to build models with remote and robust data distribution? Dan King is here from RTI and standing by to give us an overview of just such a solution. Dan, it's all yours.
Thank you. My name is Dan King. I'm a software integration engineer with RTI, and I'm going to present a short overview of RTI Connext DDS. As a quick snapshot, RTI is the largest software framework provider for smart machines and real-world systems. The company's RTI Connext product enables intelligent architecture by sharing information in real time, making large applications work together as one. With over 1,500 deployments, RTI software runs the largest power plants in North America, connects perception to control in vehicles, coordinates combat management on U.S. Navy ships, drives a new generation of medical robots, controls Hyperloop in flying cars, and provides 24/7 medical intelligence for hospital patients and emergency victims. We are the leading vendor of products compliant with the DDS standard. RTI is a privately held corporation and headquartered in Sunnyvale, California, with regional headquarters in Spain and Singapore. RTI Connext DDS is the first connectivity framework designed for the demanding requirements of the IoT. The Connext databus allows applications to exchange data in real time and provides the nonstop availability and security essential for mission-critical systems. The Connext databus enables applications to work together as one integrated system, significantly reducing development, integration, and maintenance costs. Connext is a virtual publish-subscribe databus that removes the complexity from the application software, instead handling such things as message filtering, caching, and quality of service within the communication middleware. Connext offers a decentralized architecture with no central server or services, no single point of failure, automatic failover between redundant publishers, dynamic upgrades, and a version-independent interoperability protocol. RTI Connext is a platform for distributed system connectivity. From the standard offering of Connext DDS Professional to the security plugins available in Connext DDS Secure and the low overhead available in Connext DDS Micro, we have solutions for all types of distributed system requirements. All of these products are compliant with the OMG DDS standards and are wire interoperable. In addition to the main packages, RTI also offers a wide array of tooling for application creation and debugging, from code generation to system monitoring. We also integrate with many third-party applications, such as Mathworks Simulink, and run on world-class hardware, such as the UEI cubes and chassis. With the addition of certification evidence with Connext DDS Cert, we also provide DO-178 and DAL-A certification evidence for those applications that require this type of safety certification. This is a COTS package that provides evidence for certification of the DDS middleware within your final application. Connext DDS Secure deserves some additional attention, as it allows you to fully secure your application's communication within the middleware itself. It is based on OMG DDS security standard and provides a built-in plugin to Connext with very little additional application development. This is a decentralized security solution that can run over any transport and can be customized to your application requirements. Now that we've looked at what RTI Connext has to offer, let us take a look at why Connext was developed in the first place and what problems it solves. As computers were first networked, the communication needs were simple, and simple needs require simple connections. Adding new systems is easy at first, but as the number of connected systems increases, the complexity increases, eventually dominating the system. A first-order solution is to add a broker at the center of the communication subsystem, maintaining all connections between nodes. Although addition of new nodes is a predictable task, this creates a single point of failure and can face scalability issues. As an improvement to the central broker, we have a central pub subbroker. This negates the need for explicit connections through the broker and instead allows an easier addition of new nodes. This does not solve the problem of a central point of failure and can require a great deal of development in the application layer to utilize data moving through the broker. RTI Connext, on the other hand, offers a solution that eliminates these issues. Using a virtual data bus with the communication software resident on each endpoint, the central broker is eliminated, and point-to-point communication can be established through a process of discovery. Addition of new nodes is now predictable and essentially linear. Now that we know why RTI Connext was created, let us look at how data could move through a real system. Here, UEI hardware is interfacing directly with all avionics systems, and Simulink is being used to define behavior on each chassis. Connext provides the communications infrastructure to allow data to move easily between nodes. So looking at this system model, we can see that we have a sensor here that is publishing on the green topic and an actuator that is subscribing to it. Application number 4 also subscribes to it. And then a blue topic is then published by a second sensor to the actuator and the application. A new application is brought onto the data bus that subscribes to the green topic and then publishes a new topic that the actuator and the application are both using. So in this model, we see a lot of data moving through the system all across the data bus. Now, each of these elements could be a separate node on the network, or they could be different applications running on the same piece of hardware, or even different parts of a single application running internally. And as far as the user is considered, and as far as their interaction with the RTI Connext API, it would all be identical. So if your sensor and your actuator are running on the same piece of hardware and you're using different models or using the same model within your application, you would still be publishing and subscribing to the data bus and passing information around. Now, what we're looking at here is best effort communication, which is just fine in many cases, especially when you don't have a lot of data moving across the bus. But what you can do is add reliable communication to your system. Now, the back-end communication that is done by RTI Connext through a network is UDP. Now, given that it does UDP, which is very good for best ever communication, in order to get reliable communication, you have to add some logic, which in this case is ACKs. So application 4 here is subscribing reliably to all of the data that it subscribes to. So it is providing ACKs to application 5 and to both of the sensor models. And now, if a piece of data does not make it to application 4 and doesn't send an ACK, the other applications will resend the data. And all this occurs at the communication layer. The application your application layer does not need to worry about it. We can also do filtering. So in this situation, we have the same data or the same data movement that we saw in the first example, but we want to add time and content filtering to the communications layer so as to provide data to the different pieces that need it only when they need it. So for example, with a time-based filter, that could be a control loop that only requires data at a very specific rate. And so you want to reduce the data going across the bus, and you simply use a time-based filter to keep the data coming in at that rate. The content filter could be something like a altimeter alarm, which only needs to have information from an altimeter when you're below a specific elevation. So all of this is what would normally be application layer logic that can be moved into the communication layer simplifying your application code and letting you focus on what is important at that layer, and moving a lot of the more repetitive and simple tasks down to the communications layer. All right, well, that was a quick overview, and thank you for your time. I'll now pass it back to Chris.
Thanks, Dan. Now let's put everything into perspective. In the video I'm about to play, you'll learn how easy it is to develop and deploy your model on UEI's Programmable Automated Controller, or simply UEI Pack. You'll see a real example of using MATLAB and Simulink together with RTI DDS Connext to build a model, deploy it to the UEI Pack target, and then run it. I'll bet you didn't know that UEI has our very own YouTube rockstar. Phil Zavitas, one of our application engineers, recorded this video which walks you through the process of creating your model, integrating the required functionality, generating the embedded code, deploying that model down to the UEI Pack in the form of embedded code, and then running it. And here's Phil.
How do you share information across control systems and hardware? Or even better, how do you share data amongst control models in Simulink seamlessly? UEI hardware, together with RTI's Connext DDS software, provides a flexible, robust solution, one that lets you easily acquire the valuable data that you need and share it across a variety of control systems, clients, and monitors. You can use it in the role of a publisher, a subscriber, or even both at the same time. How is this accomplished? UEI provides customers everything they need to run Simulink-generated code directly on our hardware. Now, using RTI's Connext DDS, Simulink blocks can be added to your application to send or access data via a data distribution service. This auto-generated code from Simulink is loaded and run directly on UEI's embedded, standalone data acquisition and control hardware, and provides you with a system that works seamlessly across a network of controllers and users. Let's take a look at how to generate the Simulink code for the subscriber and then the publisher. First, we create an RTI IDL file and specify the data type for the analog input channels that we're using. As you can see, we create a bus object structure with 16 variables of type double to represent the data type of the 16 channels from the analog I/O board. Now we open MATLAB software, and at the command line, we invoke the command DDS import to import the object name and data types that we created earlier in RTI Connext DDS. After this import, we open our publish and subscribe models. Each model consists of the following Simulink blocks: a domain participant, a DDS target, a publisher subscriber, data writer in the case of publishing, or data reader in the case of subscribing. Here we will build each model. The model, after a successful build, will automatically be downloaded to the target. In this demonstration, we're using two different UEI chassis, a 12-slot rectangle and a 3-slot cube. Since both models were built in external mode, we will need to connect to each device via SSH or Telnet and start the model with a -W option for wait. Now we go to the model, connect to the target, and start it. To simulate sensor data, we've equipped our analog I/O board with a loopback test adapter. The test adapter outputs 7.5 volts on all even channels and negative 7.5 volts on all odd channels. And if we zoom into the subscribe model, you'll see that we're getting data from the test adapter on all 16 channels. RTI Connext DDS is a connectivity framework designed for the demanding requirements of IoT. And just to further confirm that the data is being published correctly, we can use RTI's built-in DDS Connext utility with the following command line options. As you can see, in either RTI Connext DDS mode, the Simulink code is very straightforward. And UEI offers a wide array of hardware options, providing you with maximum flexibility.
Well, that wraps up our prepared content, and now we'd like to open it up for questions. So if you haven't already, go ahead and ask your question in the chat box, and we'll be sure to get to as many as we can in the time frame that we have. If we can't get to your question right away, we'll definitely follow up via email after the webinar ends.
So the first question we got early on was from John, and he asked if if slides could be made available. Yes, certainly. If you contact us, or we can reach out to you. I've got your name here, and I'm pretty sure we have your email address. I can definitely make the UEI content available, and I'll let the Mathworks and RTI decide if they want to let you have those slides as well. So sure, we can definitely do that. Let's see, some more questions. Question is, will this run on any of our chassis? And the answer is yes, all but the EtherCAT chassis, from our smallest cubes to our largest 12-slot military rectangle and mill systems. So the answer is yes to that. And let's see, what else? Any other questions? Oh, here we go. What UEI products do I need to do this? Well, you need three things, really. You need a hardware from UEI and our drivers in what we call our framework, our software framework, which is essentially a set of drivers. You need also a license from the Mathworks for MATLAB and UEI Sim. And of course, you would need to engage with RTI and get a license for the Connext DDS. RTI provides the blocks, the MATLAB Simulink blocks for that integration, as you saw in the videos, and we provide the UEI the blocks for the UEI hardware for Simulink. So that's what you need to build a whole system. Okay, let's see. Okay, we are getting some questions. What is the smallest hardware unit that would run on this? We have a product called the UEI Net, which is essentially a one-slot chassis, and that would run as well. And let's see. How do you connect an HMI to the RTI DDS in order to display data and control the real-time systems? Well, there's a couple of ways you can do that. You can do that directly from the UEI pack, assuming that you buy we have a CPU option that has an HDMI interface, or you can do it, of course, in Simulink. One of the tech guys, Phil, do you want to take a crack at that question, or Timur, perhaps?
I can do it. I think the key here is really to think about it in terms of the Solo X. So we have a new board coming out that actually supports HDMI natively. And from there, I think it would really come down to, being able to take in data directly from those Connext DDS sources and being able to display them via something like Qt or some other method of creating a front-end interface.
And there may be tools also from, I'm pretty sure you could build an HMI through Simulink. I'm not sure about that, or I'm not an expert on that. And RTI may have some utilities that help you to display data and control at that level. But so there's a variety of solutions there. We'd be happy to engage in that conversation with you. Let's see what else we have here. Okay, so we do have confirmation from the Mathworks that we can share their slides as well. So we will do that. I don't see any more. Oh, here's one from Christopher. Can RTI Connext DDS be used over other buses other than Ethernet, such as CAN? In this solution that we're showing here today, Ethernet is the primary method of communication between UEI's hardware and anything else it's connected to in the real world. So at least in the integration with RTI and the UEI, we are limited to Ethernet as the communication mechanism. Let's see, scrolling back down to the bottom. Okay, can you talk about how security in this simulation environment and real environment once it goes live? I presume by security, Lynn, you mean cybersecurity. Huge topic, something we'll probably do a future masterclass on. There are any number of ways to address the security question, and it's probably a much bigger topic than I can go into right now. But again, we'll be happy to engage with you on that conversation in more depth if you want to get in touch with us. Okay, any other questions? That looks like the last one. Let me just scroll up and make sure I didn't miss anything here. That looks like it. Well, great. Well, thank you very much. I appreciate everyone's time and attention, and look forward to the next masterclass.
Well, before we go, I just want to thank you, Chris, thank you, Shweta, and thank you, Dan. The few things I do want to note before we wrap things up, we are going to be holding our next technical masterclass on September 24th. This particular session will focus on application architecture. And I'd like to remind all our attendees that we record every webinar and post the videos online. You can find these archive masterclass videos on our YouTube page or on our own video page at ueidaq.com/videos. And finally, if you've got any questions, you need additional support, or you've got a suggestion for a future webinar topic, please email us at support@ueidaq.com or give us a call at 508-921-4600. And I want to thank everyone for joining us. We hope you found today's webinar useful, and we hope to see you again in 2 weeks. And as always, please stay healthy. Thank you.